What we saw during this demonstration with the FIR filter is a few things that are worth sort of absorbing over here. One of them is the fact that we can actually do driver development with real RTL code. We don't need to write a separate stub in some other language like C++ or C# in order to write a driver and test it. We get a nice Linux sysfs based interface for user space access, and we used what I'm calling the vector mode data transfer to send the samples, the data in, and to also get back the data out, right? And automatically, by just having an attribute which is defined as data in or data out, the driver takes care of keeping track of how many values are actually present over there and reading out the appropriate number based on the length parameter that it also keeps track of internally, right? Now, we can get very detailed debugging out here. We get the full Linux dmessage which corresponds to any driver related information. We get very later traces which correspond to the RTL level code. We can actually even dump out VCD files if we want to. And of course, we also get Renode logs which show us all the AXI bus transactions. So all three of these are useful and are available to us while we are debugging our entire system, right? Now, a word about performance. I showed this as part of the demo. Pure emulation can be even faster than real time in some cases because we are usually running it on something like an x86 processor, which is a faster and more powerful processor, probably with more memory than the system we are trying to emulate, and it is quite possible we can actually run even faster than real time. CoSimulation can be hundreds of times slower. It also depends on the relative clock frequency that we set. In other words, the emulated clock frequency can be adjusted to get a fast enough simulation. The problem is, at that point we are sort of making that trade-off that we are saying that we are only going to be bus cycle accurate, right? Any bus transactions, yes, should be handled properly, and whenever there is a transaction to my peripheral, the CPU will basically wait until it gets the response and only then proceed. But otherwise, I need to set the my peripheral's clock low enough that it does not interfere with the actual regular running of the processor or the internal simulation of Renode. There are many things that can cause problems during co-simulation, right? And of course, the interesting thing is we have these tools. We have VCD traces from very later, we have the Renode monitor, dmessage logs. The typical kinds of things might be very similar to what happens during regular Verilog debugging, right? Is your finite state machine stuck somewhere? At that point, pretty much the only thing that you can do is you'll need to have some kind of way of looking at the traces or the GTK wave or some equivalent over there, which allows you to look at either the state transitions or the actual internal signal transitions that are present in the Verilog code. Is the bus itself hanging in some sense? A combination of the output from the Renode monitor, which tells you what kind of bus transaction was issued, and the very later traces will allow you to say, okay, was there a bus transaction coming from Renode? What was the value that was written by Renode, or which address was it trying to read from, right? And you can in fact go directly into the Renode monitor and use the sysbus read and write commands in order to try to directly poke different addresses and see how they respond, right? So it's actually a very powerful way of sort of simulating the bus transactions as well. There are other kinds of scenarios that can happen, including things like getting stuck in infinite loops, because after all your C code which is being used in the very later is at the end of the day keeping track of an ocean of time and is running it within a loop, right? So there can be all kinds of software related problems that you can end up with, which hopefully the information that you get from all of these should be enough for you to understand and debug properly. So to summarize, what does co-simulation give us, right? Or what are the main concepts that we need to keep in mind? What Verilator does is it converts the Verilog code that you write into a set of C++ libraries. Renode then loads those libraries, not directly the Verilog RTL, but the C++ libraries, which have been compiled as shared objects .so files as peripheral models, right? It maintains two separate clock domains. There is an internal clock domain virtual time for Renode versus the cycle accurate time which is used for the peripherals. And it can actually keep track of both because Renode controls what are the clocks that are being used on each side. Right? The important thing is it's deterministic and it allows for repeatable testing. So you can actually run this through. If you find that there is a bug, you can in fact replay the entire thing. You could have detailed traces, and it's a very powerful tool for early sort of prototyping of systems. Right. So to summarize the overall purpose of this thing, there are we are basically looking at a certain kind of workflow, right? What we would typically do in the process of designing a large system would be, first of course you validate the RTL standalone, right? You use Verilator. You could also use other Verilog simulators, but Verilator has one very specific advantage, which is how nicely it integrates with Renode. That integration is the next step. You do CoSimulation. At that point, once you have the basic CoSimulation, you can actually test with software, right? You could either write bare metal software, or you could actually write a device driver. You could debug your device drivers. You could, for example, all the things like, is it parsing the data correctly? Is it making sure certain things are read only, write only? All of that can be debugged perfectly with the Renode based emulation model, right? And at that point, once you have tested with software on Renode with a co-simulated peripheral, you have a high degree of confidence that when you deploy it to an FPGA, it should work properly. There are still issues, primarily the fact that Renode is, at least the way that we have shown it so far, was being directly done at the RTL simulation level. There can be bugs that come in the process of RTL synthesis. In other words, the final synthesized output may behave slightly differently from the RTL code that you simulate. Of course, that is something that should never happen, and if it does, hopefully you will get warnings from the compiler, and you should make sure that those are sorted before you go any further, right? But once you have done all of that, this process essentially gives a fairly high degree of confidence in terms of how well it's likely to work on hardware. So the benefits obviously are, it helps you to parallelize the development process, right? People working on hardware can continue optimizing or tweaking their design, while at the same time the software group can actually start developing drivers and debugging the drivers, and not just with some kind of a model of your code, but with actual RTL code in the simulation loop. It primarily helps with early bug detection, right? And you are effectively using the same RTL all the way from simulation to the final silicon or FPGA implementation that you are looking at, right? So all of these are reasons why co-simulation is a very important tool at the system level when you are building large systems. Having said that, the obvious drawbacks of it primarily relate to speed, right? It is not in general going to be fast enough to emulate large systems with multiple RTL blocks being co-simulated, right? If any one of them is being co-simulated as RTL, it's probably okay. But otherwise, you very rapidly hit a stage where perhaps you are better off just trying to look at, can the entire module be simulated as Verilog? Of course, that is also slow. At that point, people start looking at certain things like FPGA based emulation, where they take the entire system level Verilog, try compiling that at one level into something that can in fact be emulated at a cycle accurate level. That's a different topic. We'll not be getting further into that. There are projects like FireSim and so on from the Berkeley research labs, which try to do things of, which are doing things of this sort and quite successfully. And there are a number of commercial tools also which do this, right? So what we are looking at is a much more restricted version of it, where we have Renode handling software level emulation, Verilator handling RTL co-simulation, and we put the two together and get a complete system level co-simulated environment.